Thank you for coming. We have a kind like topic for the lunch, which is archaeology. So I take you back to the 1960s. I'm very glad to be here. It's the first time I'm at J4 conference. Thanks for having me. And well, I try to explain a bit about this computer here, which is the guidance computer which flew to the moon in 1969. And well, we try to get to know what they tried, what they did with some basic hardware at these times, and great achievements, and what we can learn from it today. But before I start, just a quick introduction for spaceflight. It's still a trending topic. I think most of you follow maybe on Twitter or some other platform what's happening at the International Space Station. There are some German astronauts, Matthias Maurer, who just was there, and I think Andrew Kuipers must be a Dutch astronaut. I don't know when he was on the International Space Station, but we have the space flight or exploration of space is still a topic which is, well, current, and we have since 2000 an International Space Station, a big cooperation from the Americans and the European and the Russians, which makes experiments in the space. Of course, we all know, due to the war in the Ukraine, that maybe this cooperation does not last any longer. And maybe some of you also follow the current attempts sending another space flight to the moon. So repeat what we did more than 50 years ago. And well, it's not so easy, as we see, because they already, I don't know, 2 or 3 times started to launch this rocket. And I think the next launch attempt is on November 14th, so in some days. And that's really something which, well, leads my admiration for the people, for the engineers who made the first moon landing. We also have something I didn't discover until I was preparing this talk, that there's this Chinese space station. Actually, in April 2021, they begin to build it. And the last days, maybe some of you read in the newspapers or somewhere, that they docked the second science module, and now the station is completed and will be operated for the next 10 to 15 years. So a big space exploration is getting bigger and bigger. And well, I want to take you back to the beginnings of all this. So maybe some of you have heard of the first satellite, of the Sputnik shock. I don't think that anyone here in the room actually was alive when this happened, so it was 1957. And at this time, shortly after the Second World War, actually the Russians were the first to get a satellite orbiting around the Earth. And that was a big, big shock for the Americans, because they saw themselves as a like leading country and all these things, and it was the beginning of the Cold War time. And of course, satellites can be good. We all watch TV with satellites and stuff, but they can also be used for directing missiles and other things, so they have military use. And this big shock, like is it put in the New York Times from that day, and here's the picture of the Sputnik. This shock really, triggered the Americans, the US, to make their own space program. They already had some programs, but after President Kennedy was inaugurated in 1961, they really put a whole lot of more effort into space exploration. So Kennedy, he made a vision, he told of the goal, and that was shortly after he was inaugurated, a few months, that he said, hey, we as a nation, as the US, should commit ourselves to land on the moon and return the people safely to Earth. And he also, in later talks at the Rice University, that was one of the universities where space engineers were educated, he said, or we had this the 3 whys in the talk today in the keynote. Yeah. Why do we go to the moon? Well, because it's possible and we want to explore space, but also because it's not easy, but because it's hard, because we have to put an effort, we have to explore new things, we have to build new engineering for this. And so this was not only like a prestige effect which you wanted to achieve, but also something which triggered a whole new industry for engineering, space travel, and information technology. How did they did this? Actually, when Kennedy took the speech, or gave the speech, they already had a program which was called the Mercury program, and the first epic was to get an astronaut into an orbit around the Earth. Not a satellite, but really an astronaut, a human, which is circling the Earth. In the 1960s, a human meant a man, actually. Today we have women as astronauts as well, but then there were only men in this Mercury program, 7 astronauts, and they achieved this goal, but they were second for the second time, because the Russians had Yuri Gagarin. Some of you might remember the name. Yuri Gagarin was in April 1961 the first human to orbiting the Earth. The Americans had the first man in the space, Alan Shepard, but he was not really in an orbit, but on a lower level. And they needed some more months to February 1962, when John Glenn was the first American in an Earth orbit. So they achieved this first big goal. And then they thought, okay, what have we do to get to the moon? And of course, like you see here, here's a rocket. So it goes up, goes in an orbit, and then it lands in the Pacific, in water. And this is why here this heat shield has this form, actually, this conic form, so they don't burn up if they re-enter the atmosphere. But if you want to go to the moon, you don't have to, not only to go up, but you have to add another device which can land on the moon and fly back from the moon to the main module. So they thought about how to achieve this, and then they made a kind of intermediate mission or intermediate program, the Gemini program, because they said, okay, we need to try and build maneuvers to rendezvous and docking, which means we have 2 spaceships which dock at each other, and then you can climb from one spaceship to another. They can dock together, they can make a rendezvous, and they try to the extravehicular activity. So they wanted to step on the moon, of course. So they have to get out in space. You need a spacesuit which has to be tested, and all these things, all these technologies which were completely new and completely unprepared, they developed in this intermediate program. So a big second epic. And then finally, of course, most of you might know or may know it, that the Apollo mission that was successful, this was the moon landing 1969. I think this picture is a bit older, but still they had a successful moon landing. They fulfilled the goal which Kennedy said. We want to land on the moon in this decade, the 1960s, and they had some more Apollo missions which landed on the moon as well. And to make the effort a bit, measurable, they had 4% of the US budget spent on the Apollo program, or on the NASA total, at maximum, 4%. Today it's only 0.5%, and so that really makes transparent how big the effort was in that time. So how was the spaceship built? We had 2 modules. On the left side is a command and service module. This was orbiting the moon, so that did not land. And on the right-hand side is a lunar module, also called LEM. So this was the second spaceship, and you can see here at the top and here at the top, they could make the rendezvous, the docking, and you could, two of the astronauts could transfer from the command and service module to the lunar module and then get down to the moon and get up back again. So they had rockets and engines here, as well as here, to get back safely to Earth. And both of these modules actually had one of this computer I talk about in a short time. And they really heavily tested all these setups. So we had many Apollo missions. I did not include every one, but some, well, interesting ones. The Apollo 7 missions with all these fine badges, which give a clue what was it about. It was actually the first where the command and service module orbited the Earth. And another big step, they had the first TV broadcast, which was completely different than the Russians took it. The Americans, they said, okay, we're gonna fly in 10 days. We have this and this goals. And then they succeeded or they failed, but it was all public. The Russians, they only said about successful missions after they went. But the Americans, they wanted to, well, take the prestige, get some good news, and made TV broadcasting standard for these missions. In Apollo 8, well, the picture says it all. You get on a moon orbit, so you get out of the Earth orbit, get to the moon, cycle the moon, and get back. And it was also the first start with humans for the Saturn rocket, which is depicted in Mission 9, which was, well, I think the greatest rocket until the Artemis rocket, which is built now. And for Apollo 9, you see here this docking maneuver. So they tried all this in an Earth orbit. So if anything goes wrong, you, well, are maybe dead, but maybe you have a chance to get back alive. Or probably dead, but the chances are higher, so. And then they took it to the next level on Apollo 10. So they made a full dress rehearsal. So they went to the moon orbit with all the things which were necessary, and they had everything to land on the moon. But okay, they knew the astronauts. Astronauts, they were test flight pilots. Like real men, and everyone knew the first man to step on the moon. Everyone remembers the name, I think. What was the name? Very good. So, of course, they thought about the problem, hey, if we make a full dress rehearsal and we send 3 astronauts in Apollo 10 to the moon, they're gonna land. How do we prevent that? And, well, it was pretty easy. They didn't give them enough fuel to get back, actually. So they had this lunar module, and it had enough fuel to get until, I don't know, 14 kilometers to the moon surface. But they hadn't enough fuel to, well, I think they could land, but they couldn't get back. And so they didn't land, but it was really like, well, they didn't trust the astronauts that much in this mission. And, well, also some, they had nicknames for the spaceships, actually. And for Apollo 11, or Apollo 10, sorry, there was, I think, this one was called Charlie Brown, and the lunar module was called Snoopy, so from the characters. And for the 11th mission, the Americans took some more prestigious names. So it was Columbia for the command and service module, and the Eagle for the lunar module, which, well, made all these nice quotes possible. The Eagle has landed and all these things. So they made much word plays with it. Okay, and so with Apollo 11, they were really successful. Some of you might have seen the movie about Apollo 13. That was the planned third moon landing, and something went wrong, and a tank exploded with the fuel, and therefore they had to take the lunar module as kind of a safe boat, and then they could get back to the Earth. And actually, all these missions, they didn't lose an astronaut. There were some astronauts killed, but it was on like a mission before some of these on the base, on the surface, on the Earth. Okay, so what do we take from here? These missions, now they look like, well, everything was planned and took like the plan, but these missions were constantly refined. So they tested all these things, and they knew they want to make a mission every 3 months, but what they really adapted was, okay, what are the concrete goals for every mission? Which astronauts do we send there? They had different teams. And of course, in all these missions, they always improved the hardware and the software. So the programs which landed on the moon on Apollo 11 weren't the same, which later, with the last one was Apollo 17, I think, landed then on the moon. So always a constant improvement. Okay, so let's get to the computer which flew to the moon. That's a picture of it. Actually, that's a computer, and that's a user interface. Well, not like modern UX designers would design it, but hey, for that time, in the 1960s, this was really, and I have a simulator of it, which we can take a look at in some minutes. So it was really advanced for that time. So what did it do in the spaceship? Actually, I told you there were two. I have the picture only for the one in the lunar module, and the other one in the command and service module had some different tasks because it had some different signals that reacted to and stuff, and other programs. It had to, well, like lift from the Earth and get into an orbit around the Earth and stuff, and this one had to land on the moon. So other software and other periphery. So what did it do? This computer in the lunar module, well, the astronauts actually could control the space flight with the computer, and they did. But the computer was designed to flow well, independently. So it had some sensors, optic sensors, and inertial measurement units. So it knew about its position, a state vector, and how fast it went, and all these things. And it had a landing radar, so when the lunar module landed, so that they could see, okay, are we 5 meters above the surface or 500 meters, which is, of course, kind of interesting if you don't want to crash on the surface. And it also had a rendezvous radar to get back to the command and service module. It had the DISCI, which is a user interface, abbreviated computer display and keyboard DISCI. So it took signals from there. It controlled the engines to get down to the moon and to fly up back from the moon, descent and ascent engine, and could display some data for the astronauts. And last of all, it could get some signals from the ground station, from Houston. So receiving and transmitting signals, a state vector position. So if the signal or the data in the computer was corrupt, the ground controller at Houston could send the whole state vector up to get for the astronauts a better data. Some aspects of the hardware, mostly in numbers. These are the size in centimeters. So it's a bit bigger than a current laptop, But at that time, the 1960s, we talk about mainframes, which, well, filled like a whole room like this. And it was really great to get computer in such a small size. And it's also a bit heavier than my laptop here, so you couldn't carry it, but 32 kilograms was also really, normally computers weighed about tons at that time, so it was really awesome. Yes, a question.
Was it a single point of failure?
Well, yes, they only had one of these computers in the lunar module, so if it broke, they would have been doomed, yes. But they could, I think, and that's what they did in Apollo 13, I think, a bit control with one of the computers in both spaceships, if they had docked, control some of the other systems, but not all, because they had limited memory, I get to this point, and not all the programs were there to get it. Okay, weight is essential because the rocket, the more weight it has to lift, the more fuel it needs, the heavier it gets, and this adds up, so big achievement to get it that, well, lightweight, if you want to say. Okay, a value which is not so bad under current technologies. It had a power consumption of 55 watts, so that's comparable to my laptop here maybe. And of course, we are in the 1960s. It already had 16-bit architecture. I don't know with which computers you started. I think my first had an 8-bit architecture. Don't remember that much. But this one had 16 bits, 1 sign bit, 14 data bits, and 1 parity bit. And they had integer range from about minus to plus 16,000. Some of you might remember from university that normally there's other, or in the plus sign is one more. But in this computer, they worked with the ones complement. Nowadays, we have a twos complement. I cannot tell the difference anymore, but maybe some of you remember your university days. But integer is not that interesting, actually, because I told you that computed the state vector. Where am I? How many meters are there till I touch the surface on the moon? And of course, there you have to make many decimal calculations. And they had actually 9 decimal digits numeric precision. That's not much more than a table computer. Know how it's called? Taschenrechner? Calculator, thank you. And they needed to tweak the hardware a bit, so it was realized with a double word. So we had 14 bits and 14 bits, it's 28 bits. And then they reached a precision of 1 foot, around 30 centimeters at navigation. So you knew that like you were so low above the surface, or if you remember the docking, 30 centimeters. I don't know if I would have opened these things where there's space outside with 30 centimeters precision. But maybe it was like a design decision, so the engineer said, hey, you can get a double word, and then you get 30 centimeters, live with it. Maybe. And the astronauts, well, I told you they were test pilots, they were used to the danger of dying, actually. Okay, the computer did not have much memory, and I'm really sure that the whole room, we could not program this computer anymore to fly or land on the moon. And actually, as you see, we are not with modern technologies really able to land on the moon anymore. Maybe, we'll see if Artemis will get a success. So it had only 2,000 words of read and write memory, 4 kilobytes. And you could only save 36,000 words of read-only memory. So it had a different hardware architecture. The read-only memory, 72 kilobytes. That was your whole program code, which could be stored there. And therefore, one of the computers had the programs to land on the moon, and the other had the programs to get, well, back into the Earth. And some other limitations, because you have to imagine they invented the computer, of course, in the beginning of the 1960s, and didn't know which computer was necessary, and they tweaked their hardware like they could, but at some point you have to fix the setup because you have to test it that much to be sure that you land on the moon. So maybe it was not the hardware state of the art of 1969, but of 1962. They had only, the memory addresses had only 12-bit length. 3 bits were the opcode, so for the computer what to do. And that could only address 4,000 words. We had 36,000, so what do you do? I don't know. Many of you might remember that we had virtual addressing with 32-bit architecture, and that's the same idea here. So they did invent some memory banking mechanisms, so you had to calculate memory addresses to program this computer with assembler code. Kind of tedious. The clock rate was 2 megahertz, and it had a downlink and uplink rate to Houston to ground control with well, some bits per second, which were actually enough to get some data and state vector and stuff. That was enough. Okay, so now we take a look at the user interface, the DISCI, and we try to launch the rocket. So I have to switch, and the screen is really big. Das wollte ich noch nicht. Okay, so let's take a look. Okay, so this is a simulator. The link is in the slides. You can try it yourself if you want. So I already started it up. It's ready, so to say. And now we start the, well, pre-launch program. And you could enter commands with a verb and a noun. So it's more like addressed like the English language, but with numbers, of course. The verb is 37. And then you have to press enter to get the noun, and I have to look at my notes. The noun is 1. Okay, so now maybe you see it. Program 1 is running. What is program 1? Program 1 is the pre-launch or service initialization program. So we are still on the Earth and start like the computer for starting the rocket. And you see that here the inertial measurement unit is calibrated. So we are ready to go. And now the display switched, program 2, which means that is really the pre-launch program. And the computer is active, calculates some numbers and stuff, but, well, it's idle at the moment. So now we start the rocket, we launch the rocket. Another program is displayed, program 11, which means Earth Orbit Insertion Monitor, which means, okay, you start from the Earth, you lift up the rocket, and it should go into an Earth orbit. That was the first program at the start. And you can see here some numbers. Actually, it could display 3 values, which are at this point the velocity, how fast the rocket is going, the altitude rate, and the altitude above the start or the launch pad. And you can see the numbers are increasing a bit. And of course, these numbers are only relevant, or you have to know or remember the verb and the noun combination to know, okay, what does the numbers tell me? There's no like label which says, hey, velocity. So you had to memorize all these verb and noun combinations. And you could enter other numbers that are, let me look. For example, for the orbit parameters, which is verb 2. Now the display changes. You have verb 16, noun 44. You have other numbers with negative numbers, and also other well, the other scales. So this last line actually now is some timing information, how long it lasts to free fall. So the astronauts had to memorize all these things. Okay. Short demo of the computer. You can go back with Pro to the original display of the main running program. Yes? I get to that in a minute. The question was about the 1202 program alarm, and that will be the video about. Okay, of course, to not remember everything, they had some quick reference card in the cockpit to memorize all these things, but also for the current time, they had to state that the human, the astronaut, was the slowest component of all these stuff in the spaceship at that time already. So how was the software built? We featured the hardware a bit. The software was a real-time operating system, groundbreaking for that time. It had 7 processes ordered by priority, or it could work with 7 processes ordered by priority. It was some cooperative multitasking, so you had to say new job as a program statement that other programs could run. So you had to think about, okay, when is a good point, then I can transfer control to another program. And but that was really very advanced for that time. One of the first real-time systems at all, I think. And it also had interrupts, which we know today as well. So some timer interrupts to schedule some events or something. And of course, in keystroke from the diski, from the user interface we just saw, was also an interrupt. So the design was not that far away from today. But, and you can see that, to enter the state vector over the user interface, you had to press around 100 keys. And so they did think about, okay, when we want to update the state vector from ground control, from mission control, because we have better data. How do we do that? And they actually invented the first RPA, the first robotic process automation. So the data which was transferred or transmitted to the spaceship and as uplink data was exactly equal to the diski input you had to press. Verb, 37, enter, noun, 1, enter, value, 1, 2, 3, 5, whatsoever. So it was exactly the idea we today know as robotic process automation. Nothing is new, like you want to say. Okay, and like I said, you had to program this computer in an assembler language and hassle with this memory banking and double words and all these things. Of course, they soon realized that's not really practical, and they invented a so-called interpreter, a virtual machine. Well, we are at a Java conference. Of course, we have a virtual machine. And this virtual machine made all these computations easier. So it knew about vector and matrix data types to compute the state vector and all these operations, trigonometric and radix functions. So it was like a higher order programming language, you want to say. Index registers, stack pointers, and also the addressing, the virtual addressing was built into this virtual machine. You didn't have to compute the memory addresses yourself. It could be mixed, the code, with the executive assembly. So you could say, okay, here I have some virtual machine code, and then I have some assembly code, and transfer the control back to the executive from the interpreter. Okay, and now we want to take a look at the computer in action. And I hope now the sound is working, otherwise I try to tell you what's happening. Let me switch. So it's a wonderful project. If you have spare time at the weekends or something, Apollo in real time, you can watch 3 missions from Apollo completely in real time with pictures, videos, and the recordings from what the astronauts were saying. Okay, we try.
Roger, we copy.
At the Earth, radar up front window. Houston, you're looking at our Delta H.
Looks good.
Alarm.
Looks good.
Looking good to us.
Is it accepting it guidance?
1202.
Stand by.
1202.
Looks like it's converging.
1202 alarm. Yeah, the same thing we had.
Flight, Metro.
Go, Metro.
Throttle down. 6 plus 2, 5. Reading on the 1202 program alarm. We're going that flight.
We're going that line?
Roger, we got you. We're going
If
that
it doesn't
alarm.
reoccur, where we go? He's taking in his Delta H now.
Roger.
Roger, 330.
Did you get the
6
throttle down?
plus 2, 5. Throttle
Looks like
down.
about
6 plus 2, 5.
820.
Throttle down.
Okay, take a break here. There was a 1202 program alarm, which occurred. Actually, you can maybe see this. We are during the middle of the mission, so just short before the landing. So you see here the description where here, there, the Eagle has landed. So we are some minutes before the spaceship actually lands on the moon. So they are going down onto the moon, some 100 meters above the surface. And now this program alarm is, well, popping up on the diski. Of course, you could not, there was only a warning lamp, and then you had to enter a command to get the number of the error, and then it was displaying 1202. So they had to check the number, actually. It didn't display directly. Okay, and we have this transcript here, and maybe most of you could hear about it. The mission control says, no problem, we'll go on that alarm. Okay. Well, of course, astronauts believe mission control, and they wanted to land. No way, we are landing. Program alarm. Stupid IT computer security experts don't know what they are doing, we are landing. Okay, let's take a look what's happening. And now I can switch to here.
Okay, all flight controllers, go for landing. Retro.
Go.
Guidance. Patrol. Telcom. GNC. Ecom. Sergeant.
Go.
Capcom, we're go for landing.
Eagle, Houston, you're go for landing. Over.
3070. Roger, understand. Go for landing. 3,000 feet. Program alarm. 1201. 1201.
Roger, 1201 alarm.
1201 alarm.
Same time, we're going.
Okay, we're go.
Same type, we're go.
Flight photo right on.
2,000
Real
feet.
good. Roger.
2,000 feet. Into the eye. 47 degrees.
Roger.
Okay, another program alarm, 1201. That's just really, I don't know, around 3 or 4 minutes, 3.5 minutes before they are landing. You could see the moon already to the windows. And
37 degrees.
How's our motor talking about? It looks okay. We're okay. Roger.
Eagle looking great. Eagle, you're looking great. Coming up 9 minutes.
Go. Capcom, we're go for landing.
Eagle, Houston, you're go for landing. Over.
3,070. Roger, understand. Go for landing. 3,000 feet. Program alarm.
here you can see the moon.
1201.
The window.
1201.
Roger, 1201 alarm.
1201 alarm.
Same time, 2,000.
Okay, we're go.
And there, Houston at mission control, somebody says, we are go on that alarm. And he doesn't look that stressed, which is kind of impressive, I think. Because if I think about, hey, we are broadcasted to the world, there are 3 astronauts, there's an alarm shortly before we are landing, what am I to do with this alarm? But he was really cool and did know what this alarm meant and could say, we are going that alarm, it's no problem. This alarm doesn't prevent us from landing. And actually, How did he know? I told you that they made many simulations and many missions. And of course, alarms pop up, errors pop up. And at some mission, I don't know which one it was, but this program alarm, travel 1, travel 2, already appeared in a test mission. And then they, what's that for alarm? Okay, handbook, nothing in the handbook. Let's call the programmers. There was a whole team at the MIT. What are these alarms about? And the flight controller told Jack Garman, that was the guy in the picture, hey, I want that you know about every possible alarm which the programs might, well, give out and everything, and what we do if one of these alarms is displayed. So, what were they about? Travel 1, actually, I told you there was 7 processes which the executive could handle. Okay, what do we do if there comes an 8th process? Okay, we check the priority, and then when we discard the lowest, with the lowest priority. But, as we are good programmers, we tell the astronauts, hey, there was one more than I expected. It should never occur. There never be more than 7 processes, of course. But this exception handling, I have to put a message, no? System.out, println. Executive overflow. Okay, so really this message was about the processor, the executive couldn't handle it anymore, and one of the processes it should take out was just discarded. And travel 2 actually was the same thing for the interpreter that could only handle 5 interpreter jobs concurrently, and there came the 6th one, and then it said, okay, I cannot save this job, I cannot run this job, the one with the lowest priority gets discarded. Wasn't important, probably. And, of course, the mission control knew it wasn't important. Why? Okay, of course, they didn't know at the moment. They had this error and they knew, okay, the computer can handle the priority, the computer knows which are the most important, and the computer will do it. They didn't know at the time what was the 8th or the 6th process which should run. And they of course, they made an analysis afterwards, and this led to the conclusion that actually this rendezvous radar, which you don't need for landing, but you need for getting back from the moon to your mothership, this radar had stale data. It was a hardware issue, actually, so the programmers are not to blame, the hardware people are to blame, so to say, or a specification problem in the hardware, I don't remember that well. But actually, this radar gave stale data, and the computer computed, and the data didn't match other data, so it had to compute too much. And then it said, oh, I have too many jobs. And why was this radar on? Because in earlier missions, firstly, they flew without this radar on when they were landing. And, but they realized that if they had to abort the landing, then it was good that the radar was already on, because it's highly stressful for astronauts. You have to put a lot of buttons. All these systems have to be started and stuff. So the protocol said the radar has to be on, because if we have to abort, then we are safe. So they did have this in the protocol. Everything was fine, only there was some hardware issue. The data was stale, the computer did too much. But it wasn't a problem, because the computer knew how to handle these errors. It didn't just crash. Why did it not crash? Because they invented at that time software engineering. They actually coined the term software engineering, and we see here Margaret Hamilton, which led the team at MIT to program the guidance computer. That's an iconic picture. This is the whole source code printed out of the lunar mission. It's high like she, Margaret Hamilton. I don't know her size actually, but doesn't matter. And there were some hundred programmers, and she led the team. She invented the term software engineering because it wasn't a discipline at that time. And of course, she was also asked afterwards, what did happen? What was that LM about? And well, she replied that everything was fine. The computer was smart enough to recognize which tasks were prioritized and which not. And the alarm just meant, hey, there's something which we have to discard at the computer, but never mind. And that's a real good design of the software. She also had, so she was responsible for making the software and making the software robust. She also had a little daughter, and at that time you didn't have like a kindergarten or something. So her daughter was in the office, and they made like 80 hours a week or stuff, so they really worked like hell. And her daughter was playing with this disky keyboard, and then it crashed. And Margaret Hamilton looked at this device and said, oh, wow, what did you do? How did it crash? And she analyzed how did it work. And she came to the conclusion that her daughter started this PO1 program, pre-launch, which we said, no? You are on the Earth, pre-launch this program during the flight. So a program which is not meant to start at that point, and the software didn't cover it, so it crashed. But her advisor said, never mind, the astronauts know what they are doing. Nobody pushes a button like that. Never mind. Until Apollo 7, or I don't know the mission. Of course, it happened, and she got the team and the workload to, well, make the software robust so that the astronauts couldn't make a human error. So that's one of the first examples where the general rule came out, always take human errors into account when you're programming. And of course, another important thing is that there was a mission control, that people at the ground could handle these errors, that the astronauts and the ground control made decisions together or for their own part, which they could decide. And another example for that, I told you that this computer had a digital autopilot, so it could fly autonomously. But after all these alarms, Neil Armstrong recognized that the landing site was more like a crater, and they couldn't land there, which was like it was computed. So he took over control and slided above the surface to get a better landing site. And that was also built into this machine, that the humans had the last control over the machine. If you want to read the source code on the weekends or tonight, I don't know, it's completely on GitHub. For some years already now, I brought a short example just for this assembler code. And you're seeing here the main program for the interpreter. So the interpreter, of course, was written in the assembler language of the assembly, of the executive. And you can see here that the interpreter supported some higher order language features, like a goto or call or a conditional call or things like that. And, well, the rest of the source code I don't understand as well, so don't ask me. So what did we learn? I think, well, the hardware changes, the software changes, but the methodology or the principles, that stay. So we have this agile planning with the programs, the missions of Apollo, and the constant refinement of the plan. We have robust and fault-tolerant software with the program alarm, which really made these missions successful. Of course, and I would be very glad if that continues, we have this cooperation. The Americans, well, afterwards, they realized they spent so much money, they need more partners to make space travel possible or space exploration. And of course, you always need a visionary and people, good engineers who inspire their colleagues and staff. maybe competition is good for business. The space race, maybe we didn't never land on the moon if the Soviets didn't try as well. And of course, you have all these iterative design, simulations, tests, extensive tests, and stuff for such a mission. And one of the biggest principles, I think, which we apply all the day and every day is abstraction and virtualization. So the virtual machine, which was built here on the hardware to abstract from the hardware. Today we have some more layers, like a virtual machine and then some Kubernetes cluster and some cloud and stuff. But that's one of the core principles of information technology. Okay, so thanks a lot for flying with me through rocket history. If you have any questions, I'll be around at the conference. Yes, we have time for one more. If you I didn't understand.
Margaret Hamilton stood next to all those books of code, but I always understood that was the code that was actually on the computers during flight. That's not the case, I guess, because it's only 72 kilobytes of read-only memory.
You mean the printout was more than 72 kilobytes? Okay, maybe it was for this second computer as well, or maybe some more programs. I don't know. That I cannot answer actually. Okay, so thanks for attending. If you have any questions, I'm here for the conference. And yeah, well, happy lunch.